Now we are moving to our second speaker this morning. Petra Gruber is an architect with a passion for biology and biomimetic design, and currently she is a senior researcher at the Hochschule Rheinval in Germany and at the University of Applied Arts in Vienna. And Petra Gruber also leads her own company, transarc, in Austria. So I'd like to welcome Petra. The floor is yours. Thank you.
Thank you very much. It's great to be here. It's great to meet all of you. It's great to see such a big audience. And being back face to face is a luxury that I'm really humbled by. Ah, sorry, thank you. This is typical. We're so used to this thing now that we completely forget about it. Okay, does it work? Okay, so thanks again for inviting me, and I'm really thrilled to be here in person, seeing all of you and having the opportunity to present some of my work. So I'm kind of the person talking about biomimetics, but I've noticed that my work is actually meandering between biomimetics, which I understand as the translation of principles derived from biology or from nature in general towards technology, to a more biohybrid approach where we actually use organisms to design in the sense that Joachim just presented to us and other people are working into. So you see me here in my favorite work environment, the jungle of French Guiana on a cathedral tree. So that's what I'm most fascinated by. So I have this really strong interest in design, specifically construction, building construction, structures, materials, and biology, and I'm trying to work at this intersection. And it turned out that with my professional architectural education and with my interest in biology, I became something like a translator between those fields. And I think this is something that we need more of in the future. And I've worked in the last 20 years in this area on different platforms. Most recently at the Angewandte in Vienna, which is just a great art university that hosts the BioCool project that I will talk a little bit more about. And much of the work that you will see is emerging from the Biomimicry Center at the University of Akron, where still some PhD students are working in my biodesign lab. And I want to start with this project that kind of exemplifies the approach that I take to this overlap between biology and architecture, which is looking at the built environment in terms of biology. So I used in my PhD thesis the concept of the signs of life. So I was looking at those, what is living systems actually mean? What are the characteristics of life that we look at? And I used this filter to look at the built environment, and specifically interesting are the blank spots. So where did we not translate yet? We don't have self-propagating buildings yet, do we? So we are on the way to go there. So we are talking about living architecture and more like dynamic, responsive systems. And so I think this paradigm is a really valid one, and this touches also on one of the discussion points that we will have later on in the panel. So one of my projects was dealing with growth in general. So what does growth mean in biology, and how can we translate this into architecture and the arts? And this was a project at the Angewandte years ago with my dear colleague Barbara Imhoff, and it was one of the first big research projects that we could get in this exploration field that was funded by the Austrian Science Fund. And what you see here is a bit of a distorted scheme, but it talks about the information flow between architecture, biological role models via growth-related principles in that case. And this is kind of the essence of what we do in biomimetic design. We try to abstract knowledge from biology in order to translate it to a completely different context in technology that has nothing in common with the biological example, sometimes in terms of materiality and environment. So it's something that is also devoid of sustainability. It's an innovation strategy. If we want to design sustainably, this needs to be something that we consciously follow at the product stage. And So this is what we do. We look at both fields at the same time with kind of a fuzzy goal and a fuzzy target, and then we abstract the knowledge that we want to translate and design projects out of this. In the case of the GRAB project, the Growing Us Building project, we also had the opportunity to have our own Biolab, something that was pretty radical when we started this project and has now become a very common thing at architecture faculties. I remember it was pretty funny to discuss this at an art university with all the concerns about safety and biohazards and so on. And now we're kind of having those micromaterials everywhere. So it's really interesting how this field has advanced and how rapidly those ideas were kind of taken up and being followed by many people now. So we worked with organisms like slime mold. We grew this slime mold in 3D. We were interested in its pathfinding capacity and also managed to create scientific output by proving that this pathfinding capacity is also happening in three-dimensional space and all sorts of organisms. And we published and made exhibitions within the frame of this project. And I was lucky to work on some really interesting follow-up projects at the University of Akron in the last 5 years. And I would like to show you two of them. One is the root research that has also to do with exploring, having a structure that explores and delivers a construction system at the same time. And we are interested to abstract the morphology of coarse tree root systems for designing new foundation systems and improve coastal resilience. And two of my PhD students are still working on this, so it's in progress. We've so far managed to, with photogrammetry, image 9 different root wad models from 3 different specimens. We did this in Ohio and used local available trees that are very common, and we probably also want to use as actual root wads with coastal resilience projects. And we collaborate here with a tree company, Davy Tree, who co-funded and co-sponsored the project. So you see here, we had to take the trees out. There was no way of keeping them alive. And we used trees that the nursery would have abandoned anyway, so we didn't feel too bad about it. We felt bad about it, but at least we knew they were doomed. And so we took out those trees, we cleaned the root wads from the soil, and we also had to remove the fine root hair system because we could not capture it with the imaging technology. And we also furthered the technological methodology of doing this in the field so that we will have the opportunity to use this with just cell phone imaging, you going around meeting a root wad and uploading your photographs and using the software to create a 3D model. So this is the outcome. These are the models that we generate with a high-resolution camera and Agesoft Metashape, which is really a fancy program. And we have to do a lot of manual cleaning still because there's a lot of shadowing and those structures are extremely complex. And we hope that we can abstract information that will help us designing new foundation and coastal resilience system. So we abstract certain biological criteria like morphological data from those root wads. We use statistics to analyze, and we are just establishing algorithms in Rhino and Grasshopper to conclude principles that will help us design further. And in the following, we want to use those concepts to make new designs and then test them with 3D modeling. For some reason, it's not advancing. It is. And so the goal of the project will be to create a multifunctional foundation system that is adaptable to different situations in the built environment. There's tons of concepts for this that I just don't have the time to show you here. I want to jump to the other project that is already finished. It's a PhD thesis on leaf-shaped thermodynamics that was done by Dr. Ariana Rupp, and she's now living in Germany designing toothbrushes for a company. So it's really interesting, the pathways that the students also take with this interdisciplinary education. So we looked at plant leaves and how they evaporated water. And Ariana discovered that there is an inherent connection between the shape of the leaves and the evaporation efficiency. And you can see that on the video. So you see some of those shapes just evaporate a lot faster than others. And we experimented on this with those crude biomimetic models that are only really have a crude resemblance with what leaves actually do, which is very complex and multifunctional too. And our interest is to translate this efficiency into technical systems too. For some reason, I cannot go back. Can you help me go back? No? Yeah. And we were really lucky to use the data that Ariana has produced in her thesis in the most recent research project I'm working on at the Angewandte again. And this is called BioCool, and we want to translate this effect, this shape-function relationship that we found in plant leaves into building facades made of ceramic material for cooling envelopes. So a lot of our built environment is in climates that actually need cooling to be comfortable for people. So it's not something that is necessarily interesting for the location Vienna, but it's very interesting on a global scale, and we hope to develop a step further to cooling facades based on this principle that we have found. And we did with Ariana already poking into a 3D translation with ceramic tiles. You see some of the scientific results here. We have tested those tiles also outdoors and have also established scientific data about this. There are several publications. You see there's tiles are made and placed with sensors, and we have kind of monitored the environment at the same time to see what's going on. We've used infrared cameras to know about the trade-off between evaporation and cooling effect. So we hope that we can take this research further in the BioCool project to have a product in the end, or a product that is feasible enough to apply for a larger research funding. And this is the just a scheme of our living wall system that we had set up at the University of Akron field station to fulfill two goals. The first one was to have this thing outdoors, and the second one is also to show it to people. So it's a research and a showcase project that we had, and we also had some micromaterials that we tested at the same time with this project. And so this is just to give you a very, very short glimpse into my work, which is more kind of research focused than architecture focused. And I have to really thank my collaborators with this slide. So this is kind of the biodesign lab with my students working on the projects. And on the other side, you can see the BioCool team with the Department of Energy Design, the Ceramic Studio, and the Vienna University of Technology Building Physics Department that is collaborating with us on this cooling facade that I'm really excited about. And I also want to thank the sponsoring and funding organizations of the projects that I showed here. Thank you.